I'd like to welcome you to this installment of the Bruker AFM webinar series. This presentation today is titled Nanochemistry, Plasmonics, and Correlated Imaging. It's presented by Dr. Martin Wagner. Before I introduce Martin, I'd like to make a few quick logistical comments. First, we encourage your participation during the webinar. If you have a question, please type it into the questions dialog box on your screen. We'll accumulate these questions through the presentation, group them together, and then answer them at the end of the prepared remarks. Quite often we have more questions than we can answer in the session. In those cases, we'll be sure to follow up with email afterwards. Also, if you'd like to review the presentation afterwards or pass it on to a colleague, the webinar will be posted online within a week in the webinar section of the Bruker webpage. As a follow-up to this presentation, you'll also be receiving an email with this link. Finally, when you exit the webinar software, you'll be asked to take a brief survey. We'd very much appreciate if you take the time to complete this. This helps us to pick the topics that are most important to you and to generally make this series better. So let's get started, and let me introduce our presenter, Dr. Martin Wagner. Martin is an applications development scientist and technical lead for near-field optics in the AFM unit of Bruker's Nano Surfaces business. He received his PhD from the Dresden University of Technology, where he worked in the field of terahertz and near-field and infrared spectroscopy of semiconductor structures. Prior to joining Bruker, Martin was a Humboldt Fellow at the University of California, San Diego, where he performed the first near-field pump probe experiment and studied plasmons and graphene. Dr. Wagner is also a co-author on over a dozen peer-reviewed publications. So let me now turn it over to Martin to begin his presentation titled Nanochemistry, Plasmonics, and Correlated Imaging.
Thank you very much, Thomas, and welcome all. Thank you for joining this presentation. So I want to introduce the Inspire to you and show you some applications of this near-field imaging solution. So here is an outline of the talk. The Inspire system gives you new capabilities for your science, and it's doing this by combining nanochemical information that you extract directly from the scanning probe IR data, which means you get infrared reflection and infrared absorption of your sample at a spatial resolution which is down to 10 nanometers. So usually if you talk about infrared spectroscopy, you go to wavelengths around 10 micrometer, and 10 nanometer is 3 orders of magnitude better, so you can see really fine detail with that. I will also talk about the monolayer sensitivity that we have with this nanochemical imaging technique, and then I will focus on the combination of nanochemical, nanomechanical, and nanoelectrical measurements that you can do at the same time with the Inspire, because you can combine the SPIR technique with the exclusive Bruker technology of PeakForce QNM. And PeakForce QNM gives you, for example, the stiffness or adhesion of your samples or the modulus. So quite valuable information that you can combine with nanochemical information here. You can also get nanoelectrical information by performing, for example, Kelvin probe force microscopy at the same time. And this is very valuable, for example, if you look at graphene, because the work function that you get out of KPFM is proportional to the Fermi energy that people are interested in on the nanoscale. So you can study variations on the nanoscale of the work function. Now on the right-hand side, I'll show you a small picture where you see the overlay, so the height image and the near-field absorption signal of a polymer blend, in this case polystyrene, and PHBV, which is the biodegradable material. And you clearly see that you have high absorption at the PHBV places, which are these dots here, and polystyrene doesn't show any contrast here. And from that you can already see that you can identify where your interesting material is in your blend, in your system that you want to investigate. But I will show you a broad range of applications from polymers to thin films like organic semiconductors and graphene and others. And this package that we introduce with the Inspire is a fully integrated system. So that means you have simple, quick, automated optical alignment, and you get meaningful results. You get reflection and absorption that you can compare with far-field data to identify your system. Then also you do not need to prepare your sample in a different way than you would do for AFM imaging. So if the sample works with AFM, then you can do SPIR on it. That is a great advantage. Okay, so let's go more into detail. I want to show you first some examples before I introduce actually the technique, how we are doing that. So here, I want to emphasize the unambiguous nanoscale chemical mapping that we can perform with our instrument. You see a 4-micron image here, and you have the AFM channels that you normally have, like height and phase, and you can already distinguish polystyrene and PMMA here. But you also get 2 additional channels with the Inspire, which is the reflection channel and the absorption channel. And if you are on resonance, which means if you have your laser wavelength centered on this carbonyl resonance, which is a resonance specific to the PMMA polymer, you have a high absorption signal, shown here on the left side. If you compare it to off-resonance imaging, where you don't sit on the center peak here of the carbonyl resonance, then your absorption goes away. So this is a great way to identify which of the material is what in your image here on a 4 micrometer or sub-micrometer scale. Apart from that, I want to show you the monolayer sensitivity. On the left-hand side, you have, let's say, the ultimate monolayer with graphene, which is just 1 atom thin carbon. And nicely, you see that this graphene shows up here compared to the silicon dioxide substrate. And we will go into that deeper later on. On the right-hand side, you have an example of pentazine, which is an important organic semiconductor used, for example, in thin film transistors or photovoltaics, and we can also investigate that with our technique. Here you see the 3D overlay of height and infrared reflection far away from a resonance, but still you have contrast. And you can see that with every step you do in height, for example here, the color changes abruptly, which means that you are sensitive to each layer of your system. Now, on the next slide, I want to emphasize that we can combine the SPIR technique of Inspire with the Bruker exclusive PeakForce technique, which gives you nanomechanical information. And the way it is done is shown here in this scheme. So at each point you actually measure the approach curve and the curve that you get when you withdraw your tip. So when you approach the sample, the force increases due to repulsive forces, and then when you retract, the tip will stick to the sample a little bit until you are far away and no forces act on the tip. From this curve you can extract valuable information like the modulus. If you fit this part here to a certain model, then you can get the adhesion out of it, which is this part. You can calculate the dissipated energy from this integral under the curve and the deformation. These are valuable information on the nanoscale that you get with 10 nanometer resolution. And at the same time, you can do infrared nanochemical mapping. I want to emphasize that this PeakForce technique is a technique where you can control the peak force in a very defined way. And that means you can do these kind of measurements combined with infrared mapping on samples that are fragile. You can, or we have measured suspended graphene. You can go to powders because you do not drag your samples around, which you would do in contact mode, which you would do, for example, also in tapping mode. So you don't need to worry about damaging your sample or changing your system that you want to investigate if you go to PeakForce infrared mapping. Now, if you are more interested in this technique, you can look up our webinar from January. On the right-hand side, you see an example where we image a polymer system, polystyrene and low-density polyethylene. And you have the height channel, but also adhesion modulus and other channels combined with the chemistry channel, which gives you, which comes from SPIR. We will go into that later on. Now, there are other modes that you combine with SPIR that you can actually get at the same time with the SPIR image. And I want to emphasize that, for example, PeakForce Tuna here, that gives you conductivity imaging. And as I said before, this is impossible in contact mode. Here we have imaged carbon nanotubes vertically standing. Then you can do PeakForce KPFM, Kelvin probe force microscopy, where you get the work function on the nanoscale and with high sensitivity down to a few millivolts. This is very interesting for graphene if you're interested in the Fermi energy variations of graphene, which is the same as the work function variation. And here it's shown for graphene oxide. And we see these inhomogeneities all over the place. Then a feature of PeakForce QNM is also that you can image very fine details down to atomic resolution. So here, if you look at the scale in this picture, it's 10 nanometers wide. You can resolve like sub-angstrom features. You can see the defects in calcite. And this can all be combined with SPIR imaging. Now, let me introduce you to the actual technique. So how do we do that? And first, I want to talk about infrared spectroscopy in general. Why is it useful? And the short answer is that a lot of chemicals and also solids, they have resonances in the infrared spectral region that you can probe, and that tells you something about this system. And for like which system it is, you can identify it, or you can see what external stress or doping changes in these resonances. What we do here on the left side is measuring a PMMA infrared spectrum with far field. So you see the transmission versus wave number. 1000 wave numbers corresponds to 10 micron, which is roughly 110 milli-electron volts, just to give you an idea of the scale here. And you see certain resonances here that are a fingerprint of the polymer, in this case, that you are probing. So you can identify each of these specific resonances. For example, important resonance is this CO stretch, which shows up at 1730 wave numbers. And these far-field techniques are FTR-based techniques, for example, which have been around for quite some time, and you can use Bruker FTRs like the Bruker Tensor or Vertex to do so, to identify your system, get a chemical fingerprint, and use it also to show where are the molecular vibration, lattice vibrations, or plasmonic resonances. But the drawback with these far-field techniques is that you are limited in what you can actually resolve. So you have the diffraction limit, which in this case is around 10 micrometer. So you cannot resolve features that are smaller, which is a big drawback, because there's a lot of information hidden on the nanoscale, as we will see later on. The other drawback is that this intensity-based technique doesn't give you the electric field and the phase. And the reason for that is because you only measure absorption. You need another independent measurement, like reflection. And this is not provided at the same time in these standard setups here. Now let's look into what nanoscale IR imaging can do. And there are some papers out in the literature. I want to show or highlight some aspects. For example, this work by Markus Raschke shows you a polymer, block copolymer between PS and P2VT. And what you see are very fine structures here that show up on the nanoscale. You see a resolution of down to 8 nanometers here for this polymer. Now on the right-hand side, there's a work of Andy Huber. He quite nicely images a semiconductor transistor, shown here on the left side, at 2 different wavelengths. So in the infrared, and then he even goes to the far infrared spectral region. And you can nicely see the electron distribution here, the electron doping, which is in this case sensitive to the probe energy. Then an example from biology would be a tobacco mosaic virus that Markus Brehm has imaged. The important thing is that he looked at the amide 1 resonance of the shell of this virus, which shows up at 1660 wave number, so he sees a resonance, and this is the reason why he can image this virus. Another recent example would be phonon polaritons that have been imaged on the nanoscale in these boron nitride nanowires, and you nicely see the field distribution of the phonon polaritons that change with wavelengths here. And look at the scale, so the width is below 100 nanometer of these nanorods. And the last example I took is from geology. Here, Gainsforth looked at the distribution of certain silicates in a comet dust particle, which is very small. And you can identify how your silicates are distributed here. Now, all these examples show you variations of some properties, optical properties on the nanoscale. And if you would like to image that with an FTR, with normal far field techniques, then you would have a spot size roughly like this. If you look at the polymer scale here, 400 nanometers, then we can show this large spot here to scale. And that means you average over all these important properties of your sample. So there's a lot of information hidden on the nanoscale that you want to access. And SPIR, so scanning probe infrared with the Inspire, is a technique to do so. And here I want to show you the implementation, how it's done. So you have an optics box with an interferometer on the left side. And from there you have laser light focused down on an AFM tip, on the apex of this tip. Below the tip you have a sample scanner, which means that you move actually the XYZ stage of your sample, and you don't move the tip. The tip is fixed in space. In this way it's aligned to this incoming beam all the time. And then what's happening is that this tip gets polarized and you have a lightning rod effect, similar to lightning striking into the top of the Eiffel Tower. You have field concentration at the very top, or in this case the very bottom of your tip. So you have very high field amplification here in the near field region between tip and sample. And these near fields can be influenced by resonances of your sample or by the metallic character of your sample versus the semiconductor character of your sample. And then these near fields are scattered back into the far field by this antenna. So this tip actually acts like an antenna, and it's scattering a part of the near field back into free space. And we detect this far field scattering and bring it back to the interferometer where we perform our analysis. Now, the different components have different functions here. So the tip gives you a localization down to 10 nanometer, which is roughly the tip radius. So the resolution is determined by the tip radius. And this technique is independent of the wavelength that you are using. So it has been shown that it works for terahertz frequency, but also near-infrared frequency. but infrared frequency already covers a broad range of interesting resonances and physics or chemistry. Now, this part is responsible for doing the imaging, and you can combine it with PeakForce, QNM, with KBFM, and lots of other exclusive techniques. And the interferometer, of course, is used to give you the infrared absorption and reflection in the end. Now, let's go into more detail. Actually, what do we detect? How do we get the near-field information out of the backscattering? So on the left side, I've shown you again a schematic of the interferometer. You have your light source, which is, in this case, it's a tunable QCL laser, but the customer can choose like which wavelength. And then we split this light in an asymmetric Michelson interferometer. So you have your beam splitter in the middle. Part of the light is going to the tip and it's back reflected and then led to an MCT detector. But the other part of the light coming from the laser is going over a reference mirror and reflected back to the MCT detector. Now, you do have also a large background signal because your tip that is illuminated, even if it's far from the sample, gives you backscattering. Also, the sample gives you some backscattering. If you go close to the sample, then additional to this backscattering light, you have near-field information, which are these tiny blue arrows here. So we need a way to get the near-field signal out of that. And actually what we detect with the MCT detector are not fields. We detect intensities, so we get the interference of all these fields, reference field, background field, and near field. But near field is what we want to look at. So we have to extract that. And if we calculate this term here, we end up with this long term here, which looks scary at the beginning, because we are also only interested in the near field here in the first term. We want to find a way how to get rid of the other terms, and it's pretty simple to do so. And what we use is shown here on the right-hand upper side. We use the fact that if we modulate the tip, so if we oscillate the tip up and down, then the far field contribution will more or less be linear. And in time, you would see a sinusoidal oscillation at the same frequency that you drive your tip up and down. And if you do an FFT Fourier transform, you see only the spike at the first harmonic, which is the tip oscillation frequency. Now, if you look at that, if you look at the scattering from the near field, then you would see that if you go close to the sample, so at small heights, then you have a large near field contribution. But if you go far away, then the near field contribution drops. And this means it's a highly nonlinear signal compared to the far field signal. So in time, you have these spikes. You have high signal when you're close to the sample. And if you Fourier transform that, you have a lot of higher harmonics that are not present in the far field backscattering. So this is the way to go. We want to look at higher harmonics to suppress these terms here that are not modulated at higher harmonics. So we get rid of them. Now, this second term we get rid of by looking at the size of EREF, of the reference field here, compared to the background field. And the reference field is something we control. So it's much larger than the backscattering of the small tip and the small sample area we illuminate. So this term is negligible also. And in the end, we just end up with the first term here, and we are interested in the near field, both in amplitude and phase, which is different from what you get in FTR far field techniques. You only get intensities. And we are free to choose the reference field here. That gives us the flexibility to get reflection and absorption out of the measurement. If we choose the reference phase to be 0, it means that we only detect the in-phase contribution of the near field. And if we choose it to be pi/2, then we get the out-of-phase contribution, which is the absorption. Now, I want to emphasize that on the next slides, here we see the effect of the resonance on the absorption. So we measure the outer phase contribution, which means the reference field is, or reference phase is set to pi/2. And if we are on a resonance shown here with our center wavelengths, so the green one is the absorption curve, which is calculated, and the blue one is the reflection curve calculated. If we are on resonance, we have strong backscattering. But if we are off resonance, we only have small backscattering. And that is the reason why we can distinguish materials in the absorption here in this outer phase measurement mode. Now in reflection, we have to look at the blue curve here, and we see that you also have distinct maxima and minima. So below the actual absorption position, you have a maximum of the reference. That means you have large backscattering at this frequency. And if you go above the resonance, above the absorption here, you have a minimum in the reflection, so you have low backscattering in the reflection channel. So in this case, you can also get an idea of where your absorption lies just from the reflection channel alone. And beyond that, the reflection channel gives you information about the film thickness. So we have looked at the organic semiconductor pentacene before, where we could see that the different layers show up differently in reflection. You can get information about the connectivity or plasmonics, for example, in graphene, just by looking at the reflection of your sample, and we will go into that deeper later on. And okay, the last part, graphene, I can show you here already, where we plot the theoretical reflection and absorption that you would measure with the Inspire in the infrared range for graphene, and you see distinct features depending on frequency, and this is something where you can distinguish and characterize your material. We looked at polymers before on the left bottom plot, and also if you look at other systems like metal to insulator transitions, or transition materials like VO2, vanadium dioxide, in this work of Liu et al. Here. You see these metallic domains that show up brightly in this insulating matrix. And if you increase the temperature, you see more and more of these domains. But here you actually are not interested so much in the resonances of your system. You just want to see a reflection change. You want to distinguish metallic domains compared to low reflective insulating domains. And this you can easily do. So both reflection and absorption are important, and both together that you get with the Inspire system enable you to characterize virtually any material. Now, let me introduce some capabilities of our techniques. So first, I want to show you that we have very high spatial resolution, down to 10 nanometer. And this is highlighted here. We have silicon, so the bright area is silicon, and silicon dioxide test grating. If you zoom in, you see these inhomogeneities in silicon. And if you zoom in further, you can see them even better, and we have a resolution down to 10 nanometer here. So very high. Now, I mentioned before reflection and absorption. I already mentioned polystyrene and PMMA, that you can nicely distinguish in reflection and absorption here. If you are on resonance, if you are away from resonance, then that absorption doesn't show up. And that also means that you have always contrast in reflection. In absorption, you have to sit on a resonance in order to see something. And that means you can use the reflection channel also for alignment of your system. So you want highest signal in the reflection channel if you're sure that at this wavelength your system doesn't absorb, otherwise could be a problem. But this is something that Inspire will give you. Now, the reflection channel alone enables you also for identification because you have these minima and maxima in the reflection. That tells you something about where your absorption sits. Now, Inspire is also a technique to distinguish different phases of your material, like an amorphous phase versus a crystalline phase. And what we show here is a normal CD rewritable media and the DVD rewritable media. And you see in the height channel these trenches in both cases, but you don't see any dots in the height channel here, which would be the case if you look at ROM media, where you actually have dots that are the bits, that are the data that you have on your DVD. But what you see in the reflection channel is that some areas reflect less than others, and these are the areas that have been made amorphous with a laser. So you can nicely distinguish the data here, and it also gives you an impression that you have a topography-free contrast here. So you don't see the edges that you have in height. You don't see them very well, at least. On the next slide, I want to combine PeakForce QNM with simultaneous infrared nanochemical mapping in a PS low-density polyethylene polymer blend. And what you see is normal height channel, but also adhesion and modulus, deformation channel. And from that, you already know that some of these materials are harder than others. Like this low-density polyethylene can be compressed or deformed much more than the matrix. So you have a way of identifying the systems, but sometimes you have more than just two systems, or you have systems that show same nanomechanical properties, and then it's good to have another channel, another way of actually distinguishing or characterizing your material. And in this case, simultaneous infrared mapping would be very good, and Inspire gives you this technique. So we can combine Inspire with these techniques, but it's also quantitative what you get out of that. You can get the quantitative values in gigapascal for the modulus, or in nanometers for the deformation, and also for the infrared reflection, you get the same quantitative values. Now, we can combine infrared mapping not only with nanomechanical mapping, but also with electrical mapping. Here we combine it with KPFM. We look at a 20 micrometer large sample. We have aluminum on the left side, then we have a silicon trench in the middle and gold on the right side. Already from adhesion, you see some contrast, for example, between silicon and aluminum. And then if you look at the reflection channel down here, taken at the same time, you can clearly distinguish gold from silicon, but also silicon from aluminum a little bit. But if you add KPFM, you see that you also have a quite different work function for all these materials. And this is also a quantitative measurement, so you can extract your work functions of your sample in millivolts. So what we look into here is this interesting feature in the potential. So we have in the height channel this little particle here that also shows up in adhesion, but that does not show up much in reflection. But in the potential channel, you have this large crater here. And we think that this is a charged particle that locally changes the potential, the work function of your material. So this is a nice technique. You can combine nanomechanical, electrical, and nano-optical measurements. On the next slide, I want to emphasize that we can really map different materials, organic as well as inorganic samples, and also mixtures of these samples. On the left-hand side, you see imaging especially infrared absorption at the carbonyl resonance of a block copolymer. So we have polystyrene and PMMA on a length scale of 500 nanometer, and you see nicely these little domains of the polymer. You can also image hard materials like silicon and silicon dioxide, shown here in this test grating. You can look at hard fibers, shown here, optical fibers, where you see the fibers in reflection also compared to the epoxy around it, and you have some dirt or some epoxy on top of the fibers here, shown up in the infrared reflection channel. Now, we can also combine organic and inorganic materials, shown here, where we look at the polystyrene and low-density polyethylene sample. But here, there's a region where we can actually look down to the substrate, to the silicon, in infrared reflection. That's an infrared reflection image. And we see that silicon is highly reflective in this case. So from that, you can already distinguish the different materials. And I want to emphasize that the SPIR technique does not require photothermal expansion of your sample. So you're not limited by that. You can look at these different organic and inorganic materials. You do not need a special sample preparation. If it works with AFM, then it does work with the Inspire technique. Then you are not limited to samples that would withstand high forces. So you can use samples that would not be possible to be imaged in contact mode or in tapping mode, because you can combine our technique with PeakForce Tapping, which means you control the interaction force between your tip and your sample. And this is a nice way to image, for example, polymer nanoparticles, or you can go to suspended graphene, and you don't have to worry that you damage your graphene sample. And in contact mode, for example, this block copolymer would suffer a lot. You would just drag around these polymer, these little guys here, and you would also blunt your tip on this test grating in contact mode with time, which is not the case if you use PeakForce Tapping. So the nice combination gives you more flexibility in what you can look at. Now, the last part of this talk will be about graphene. So we have seen this picture before where we calculated the SPIR reflection and absorption of graphene in the infrared. And you see these certain features here. So this feature is 2 times the Fermi energy. Then the width is given roughly by the scattering rate in your graphene. And these 2 properties, Fermi energy and scattering rate, are properties that people are interested in on the nanoscale. And SPIR gives you a way to actually reveal these features. Also, the number of layers would heavily influence the height of the absorption and reflection here. So you can distinguish the number of layers with this technique. And there are 2 regimes in this infrared plot that I show you here. On the left side, we have the plasmonic regime, where we go into later, and on the right side, we have the universal conductivity, universal optical conductivity regime, which means that these properties, absorption, reflection, are constant if you go to a higher frequency. Now, let's look at the universal conductivity regime first. So we tune to a wavelength of 1730 wave numbers. And what we get is a reflection image shown here in the middle. And we can nicely distinguish single layers, which is the black one here, compared to the SiO2 substrate. Then you have bilayer here, trilayer, and 4 layers. So on the bottom you see a line cut through these layers. And you can distinguish these layers with 10 nanometer resolution in the reflection channel, where you are far away from any plasmonic resonance of your system. On the left side, you see an AFM image of the sample, where you also see some steps, so we are sure that we measure the right number of layers here. And KPFM at the same time would tell us the work function, or equivalently the Fermi energy of your sample. You can get that out of the KPFM measurement. If you zoom in, we can do nanomechanics at the same time. We get the topography, but also the adhesion, and see these small features in the nanomechanical channels. And these are wrinkles of graphene, so it's not perfectly flat here. You have some defects. It's wrinkled. If you look at the infrared reflection, so you zoom in a certain area here, and you see that we can distinguish the layers, but one layer, the single layer, has an area which has a 2% lower reflection. So quite a tiny change in the reflection of a material that is only a single layer atom thin. So we are quite sensitive. And this area, the 2% lower reflectivity that we see here, corresponds to an area where we also see an increase in the D-band signal if we do Raman. And that gives us a hint that this area has some defects. So we are probably sensitive to defects in this area with the SPIR technique. Now, the last point is, let us go to the plasmonic regime, where we go to low frequencies, 870 nanometers wave numbers. And let me briefly talk about plasmons in graphene, which are very important and studied in the last years, because plasmons are a way to confine infrared energy to small sizes, so you can confine energy to the nanoscale and in form of a plasmon, and then you can bring some particles or any biomaterial or chemistry material you're interested in. You can bring that close to it, and you have efficient nanosensors. And plasmons are also interesting for photovoltaics, or if you want to transfer energy from one point to another, then plasmons might be a way to do that in the future. But with graphene plasmons, the problem is that you have to obey the energy and momentum conservation rule. So you have this dispersion here, which is square root-like. And if you want to excite or detect the plasmon, you cannot do that easily with far-field light, which has a momentum close to 0. But what you can do is you can pattern your sample, which has been done in this work, via nanostructuring of your graphene. But the problem is, for each wave vector Q, you have to have a different structure, so a different sample. And also you change the properties because you add edge effects. But if you go to SNOM, to the SPIR technique, then you have scattering from this small AFM tip, from the end of the tip. And that gives you a broad momentum range that's highlighted here. So you can easily and intrinsically, by using this technique, you can access the plasmons. You can launch them and detect them. And this is shown on the right-hand side, where people imaged a graphene triangle here. And what's happening is that the tip itself, while it is scanning over this triangle, it's emitting a plasmon in the graphene. And graphene will support the plasmon. It's traveling in graphene and will be reflected at the interface here. And then it's coming back and is back scattered into far field. And what you end up is a standing wave, which gives you an idea about the graphene plasmon properties. And this is something we can easily do with the Inspire system. So if we zoom in here, in this part of a single layer, then we see this edge, and we see that we have a plasmon fringe here. If we go to a different sample, which more resembles this triangular shape, then we also see these nice fringes here at the edge, and we have high concentration of plasmon energy, or energy here at the end of the tip, and also at this defect here. But nicely, in both channels that you get with the Inspire system, you have reflection and absorption. In both channels you see the plasmonic fringes. and people can analyze the plasmonic fringes, and you want to know about how far do they travel and things like that, and what's your amplitude. You can do that with Inspire easily. What you can also do easily, and this is the last slide, is you can go to very high scanning speeds without actually destroying or compromising your measurement, destroying the sample. That's not an issue here. So here at 1 Hertz, you see the plasmon fringe. You see it nicely at 4 Hertz and also at 10 Hertz. And the periodicity of the plasmon stays the same, so same plasmon wavelengths. The only thing that changes, of course, is the signal to noise if you measure faster. But this is very high very fast imaging, very high velocity imaging, and you have no significant loss of spatial resolution. And importantly, you do not damage your sample. And this is only possible with the stability of a great AFM. So what you get here is a very nice AFM combining all the modes of nanomechanical and nanoelectrical mapping. But at the same time, you get the added value of nanochemical like identification, nanochemical imaging from the SPIR technique, which gives you sub-micron down to 10 nanometer spatial resolution. And at the same time, meaningful results. You get reflection and absorption that you can compare with far-field databases, FTR database, for example. Now, I've shown you these capabilities of our system, and I've shown you a broad range of applications. So we can look at polymers, you can look at thin films, organic semiconductors, graphene, of course, and it's a nice package that you get. And I want to emphasize that you can measure samples that you cannot easily measure in contact mode. So you don't drag around your polymer nanoparticle, or you do not damage your suspended graphene sample. And with that, I want to end. So I hope I could show you what Inspire could do for your research by combining all these different exclusive modes to Bruker. And I thank you very much for your attention here. And I hope you have some questions, and I give back to Thomas. Thank you very much.
Thank you, Martin. Thanks, and thanks everybody for attending. We do have a number of questions here. Give me just a minute to go through them. We will certainly answer some of them right away, and if we don't get to yours, we will definitely follow up with email afterwards. One question that came in was about whether this technique would be useful for samples that include polymers with embedded nanoparticles or other objects.
So I would say yes. It partly depends on which nanoparticles you are talking about. So I assume that would be a gold nanoparticle. Then you would have high reflection, and it also depends a little bit on the size of the particle. But I would assume that you can measure this with SNOM technique. It depends a little bit on the depth of your nanoparticle. So if it's below, let's say, 50 nanometer in depth, then you might not see a big contrast, because SNOM or SPIR is a technique that can probe down to 50 nanometers or sometimes up to 100 nanometers, depending on your system. So people have shown that you can image the electron distribution in doped silicon down to 100 nanometers. So it depends a lot on your system and the size of the particles. If it's too small, if it's like a nanometer, then it might be difficult. But on the other hand, if it's something that is highly reflective and the surrounding polymer material doesn't show much in this region, like a resonance, for example. So if the background signal from your polymer is small, then you have a high chance that you can use the system with your special sample, but it depends on the details.
See a question coming in here, whether the instrument would be suitable for very soft materials, lipids or proteins. I should say the measurements we've shown here were done in air, not in liquid. The instrument, I would say is suitable in that the technique itself operates intrinsically in tapping mode, and we've also shown that we can operate it in PeakForce tapping, using that for feedback. So say we're well set up for very soft samples where you might have to use tapping, or where you would only be able to use PeakForce tapping and where you couldn't use contact mode. Let's see, and another question here, what's the excitation bandwidth, and maybe related to that, what's the line width of the IR source?
The excitation bandwidth, this is something that the customer chooses, so we provide you with a broad range of laser solutions, and you can go down to, I think, if you use a QCL, you can go down to around 870 wave numbers. If you use a CO2 laser, it would be also around this range, and you can go up to like 2,400, 500 wave numbers, maybe even above. You can continuously find lasers in that range that are tunable for each laser in a range of around 100, sometimes to 300 wave numbers. So we can cover a big deal of the infrared interesting spectral region. And yeah, that we would offer with the system.
Yeah, it's a narrowband CW laser.
Yes, it's narrowband continuous wave laser, and the spectral width would be far below a wave number. So I think it's 0.01 wave numbers. So you get very high resolution with this technique.
Question of what size objects, what size samples fit in, and how do you prepare these samples? The sample requirements are the same as for the multi-mode AFM. There's really not a preparation beyond that, so same sample widths and thicknesses as you would have for our multi-mode AFM. There's a somewhat related question whether this is available as an upgrade to the multi-mode. It is not at this point available as an upgrade. It's a separate complete package, although the AFM is based on the multi-mode AFM. We have a question on the sensitivity. What is the minimum thickness, and what's the sensitivity to thickness differences or to film thickness of the technique?
No, that's a good question. So we have shown part of it already. If you look at graphene, which is only, I think, 0.3 nanometer thin, or no, 0.03 nanometer, so it's quite tiny, and you can distinguish that, and you can count the layers in graphene with this technique. So we have really sub-nanometer, sub-angstrom sensitivity in the thickness of a material. Also for this pentacene film, which is only beyond a few nanometers, you have sensitivity to each layer. So from that point of view, you can really image and distinguish materials that are very thin, and you get nice contrast with our technique in reflection and also in absorption. So even if your sample doesn't show absorption in this range, you can still distinguish different layers just by looking at the reflection that changes with the numbers of layers.
Question, what are the infrared power levels incident on the sample? What's the estimated spot size of the laser on the sample?
Well, that's also a good question. So spot size would be around, I think, 10 to 20 micrometer, something like that. So you have a spot that is, of course, limited by diffraction, slightly larger. But the power levels are not very high, so let's say 1 milliwatt and below that on your sample. So you don't risk to damage your sample here. I mean, you don't have a high power OPA, for example, amplifier system that would burn your sample, and you are not using a technique here where you rely on excitation of maybe photo-excited expansion. You don't need that here, so you don't need high powers. this is only small power in order to probe the sample properties, and it's of the order of a few milliwatts at most. But we haven't seen any sample damage so far in any of these measurements.
Regarding KPFM, do you have recommendation for surface preparation? Also a question, were these measurements done in vacuum for the KPFM?
Well, for KPFM, we didn't do anything in vacuum here, so it was normal AFM, KPFM mode. And as I said, it's combined with all the other modes, so we do not have a special preparation of the sample. So you can use any sample that fits in our AFM, and you do not need to prepare your sample, especially for KPFM. And also, yeah, you need just a metallic probe. That's the only requirement.
Right, and so it can be the same metallic probe as for the scattering SNOM.
For the scattering SNOM, yeah. That's the requirement for the SNOM tips, that you have a tip that is metallized. But it nicely, it can be nicely combined with the other requirements. For example, for the nanoelectrical measurements, that needs a tip that is metallized.
I could add that for this we did the KPFM in completely ambient conditions. We can do KPFM on many of our instruments. We have also done comparisons ambient versus in our glove box based systems. So we have that comparison too. It's a bit of subject of a different webinar, but that's something we can do too. And another related question on the KPFM measurements: did you really do the KPFM and the SNOM at the same time? And don't you need to null the oscillation for KPFM? How can that be done?
Yeah, I mean, it's you get each or you get all the information not at the same time. Yeah. So for the combination of PeakForce and SPIR, for example, you do the PeakForce tapping, and then in the next line you do the SPIR measurement, and that is the same for the KPFM. So you have to have that in, well, consecutively. But this measurement, I mean, you lose, the only thing is that you lose time by doing this measurement, right? So if you want to combine all these measurements, if you want to have nanochemical, mechanical, and electrical measurements at the same time, you need to sample the line like 3 times.
I should add, we can do the KPFM measurement in AM KPFM as well as an FM KPFM, where we do mechanically actuate the probe. You see, yeah, another question on how deeply do you probe with the technique? How deeply into the sample?
Yeah, that's a good question. So we can go down. So this technique can go down to 100 nanometer, and it strongly depends on which material you look at. If you have something highly absorbing, where the near fields are absorbed before you reach your whatever you want to look at in the 100 nanometer depth, then you have a small signal. You can probably not probe so deeply. But people have shown that you can map, for example, gold discs below a polymer in, I think, 50 nanometer depth, or you can look at doped silicon trenches in 100 nanometer depth. So it depends on your system, but in general, 50 nanometer should be no problem in depth resolution with SNOM. That you can that you can probe 50 nanometer deep structures.
One question here on what's the typical time scale to acquire a full image, say a 256 by 256 pixel image with good resolution. How long does it take to acquire such an SPIR image?
So it also depends on your system. I mean, in this case, we show that we can image quite fast in 30 seconds, and we are not limited in speed. For some AFMs, you might be limited because you think you damage, and you actually damage tip or sample if you would scan at these high speeds. So in general, I would say just a few minutes that you need for a good image with good signal to noise. But then again, it depends on the features that you look at and the strength of your, let's say, absorption features that you look at. But in general, just a few minutes for these scans. And you can accelerate it if you go to 10 Hertz, but then you lose in signal to noise.
Okay, thank you, Martin. And we have a few more questions, but we are over our time limit, so we will follow up on all the remaining questions with email. Thank you again, everybody, for attending. When you get to the exit survey, please do take the time to fill it out. It helps us a lot for these webinars. And we hope to have you again listening to our next webinar in our monthly series. Thanks. Bye-bye.
Thank you very much.